In this example problem, we will be calculating the estimated capacity P of the beam shown using both the simplified shear equations and the Strut-and-Tie method from AASHTO. We're not going to use safety factors because in this example we're analyzing the system and we want to see how close the Strut-and-Tie procedure estimates the actual capacity. The beam has a shear span to depth ratio of 1.85 on the one side of the beam and a shear span to depth ratio of 2.5 on the other side of the beam. You can see here the test setup is it's an inverted, simply supported setup where we have the supports at the top on the ends and 3 point loads on each ledge of the member. So it's an inverted T-beam. And you can find more details of these tests at the publications that I show on the screen. Details for the beam, the section, and some of the material details are shown on this slide. So you can see that it's an inverted T-beam. So we have ledges where the load is placed. So the load, or these beams are loaded on the ledges. You can see this is a section view of our ledge section. You can see that we have number 4 bars in the vertical and horizontal direction spaced at 6.5 inches. And you can see some of the other details. So the area of our of our steel, the location of our primary longitudinal steel, and then also some of the other information on our section, the gross area, and the moment of inertia, and then also our shear layout, so shown here. You can see the measured values for our concrete strength, for our yield strength for our different size bars are shown in the table to the bottom right. We'll start this example by finding the sectional shear strength using the AASHTO LRFD simplified procedure. So the first thing that we need to do is figure out the depth of our tension steel. So here, the overall height of our section is 42 inches. The distance from the bottom to the centroid of our tension steel is 4.36 inches. That was given on our previous slide. So we can see that the depth of our tension steel is 37.6 inches. So the dV that we'll use in the AASHTO procedure, we're going to assume is the max of 0.9 dE and 0.72 H. I didn't give us any details on the nominal strength of our section, so we're going to use the maximum of these two values. So the max is 33.8, so that'll be our dV that we use. The simplified procedure for non-pre-stressed sections assumes an angle of compression of 45 degrees and a concrete efficiency factor of beta equal to 2.0. So we're going to use those in our VC expression and VS expressions. So we can start by finding our concrete shear contribution. So our VC is equal to 0.0316 times our beta, which is 2.0, times the square root of 5.7 KSI. So in AASHTO we use KSI, and in ACI we use PSI, times 21 inches, which is our web width, and 33.8 inches, which is our dV. So we'll get this to be 107.1 kips. Next we can find our steel contribution. So our VS is equal to our AV, which we have here in the shear span, 2 times 0.2 square inches, the area of our number 4 bars, times 60 KSI, times 33.8, times the cotangent of 45 degrees, divided by our spacing, 6.5, gives us a VS here of 124.8 kips. So we can add these together then. So 107.1 plus 124.8 will give us a total shear capacity of 231.9. And we can compare this to our limit, 0.25 times 5.7 KSI times 21 inches times 33.8 will give us a limiting value here of 1,011 kips. So we can see that our capacity VN is less than that limit, so that'll be our total shear resistance. Next, we're going to start our Strut-and-Tie method analysis. So the first, shown here are the different steps that we'll do in a typical Strut-and-Tie method design. For our analysis, we will already have these first two steps completed. We already know our loads; those are given, and we have been given our member size. So, and we've also been given the reinforcement, so we'll do an analysis using the Strut-and-Tie method. But anyway, these are the 12 steps that we'll typically use for the Strut-and-Tie method, and we'll work through on the following slides. The first step that we're going to do is we need to figure out what are B and what are D regions. So what are our Bernoulli or beam regions, what are our deep beam regions? So we need the depth, our D, which we found before to be 37.6. And now we need to go a distance of D away from any load points, any supports, or any geometric discontinuities. So we have a support here. So we need to go a distance D away from there. We have a geometric discontinuity here, so we need to go a distance D away from here. We have a load here, distance D away from there. Another load here, D away, another load there, D away, and so forth. So you can see when we end up getting all of our Ds, we'll have that the entire beam is a D region. So our entire beam then is going to be a D region. So for this beam, we're going to use the Strut-and-Tie method to analyze the entire beam. Our next step is to develop a Strut-and-Tie model for our D regions. In an inverted T-beam, we're going to have a three-dimensional model. So we need to get the load from our ledges into the beam. So we have diagonal struts here, and then we hang them up through our hanger ties there. So we have a cross-sectional model to get the load from our ledges into the beam, and then we have our longitudinal model to get the load from the hanger ties into the supports. So we're going to look at our longitudinal and cross-sectional model, but these two models make up a full three-dimensional model as shown here. So, and also note in these models, our red elements are all tension ties, and the blue elements are all compression struts. The next step is to calculate our strut and our tie forces. In order to do this, we need to figure out our exact geometry for our Strut-and-Tie model. And note that in this example, we're going to focus on the longitudinal model. So there would also be a cross-sectional model, as I mentioned on the previous slide, but in this example, we're just focusing on the longitudinal model. So the depth of the steel was given to us and is set by the location of our longitudinal tension reinforcement. So we had our two layers of number 11 bars, and that gave us a D of 37.6. The centroid of our kind of top line here, BDFH nodes, is we can determine by our stress block depth. So if we take a cut at any point, we would be looking at the stress block depth. So we would just have our normal stress block, with our tension reinforcement and our compression reinforcement. So we can find our stress block depth just through equilibrium and our regular principles in normal reinforced concrete. And I'm going to assume here, just for simplicity for this example, we're going to assume that the compression steel yields. So the compression steel probably doesn't yield, which will affect the stress block depth, but in this example, we're just going to assume it does for simplicity. So here we can find our stress block depth of 6.26 inches. And then we can use that to determine the depth or the distance between our top node line, just B in this point, and the bottom node line A. So it's our depth minus beta 1C over 2, which will give us 34.5 inches. So that's the distance between the bottom and top lines. The horizontal distances, many of them are already set from our loading and support points. So for instance, the distance between I and J is set by our load and support points. Again, between G and I, support points, E and G, support points, load points. The distance between A and C and E is going to be determined based on what reinforcement is engaged in that vertical tie BC, which we're going to look at in the next slides. But we need to use those dimensions here to determine our forces. So I'm including them here. Our next step is to use our 25-degree rule near the support and our 45-degree rule for loads on ledges to determine the width of our tie BC. So the total distance between A and E is 94.1. The distance between A and our edge of the 25-degree rule is going to be 42 inches, our overall height, times the tangent of 25 degrees, which is 19.6 inches. The distance between the load point and the edge of our 45 degree is half of our bearing, so 16 divided by 2, plus 21 inches, which is our ledge height, times tangent of 45 degrees. So this will be 29 inches. So then the total width of our tie BC is our distance between A and E, so 94.1, minus 19.6, minus 29 inches, which gives us 45.5 inches. So then our distance between A and C is just our LA 25 degrees, which is 19.6, plus half of our tie width. So 45.5 divided by 2, which will give us a distance of 42.4. And then the distance between C and E is 94.1 minus 42.4, which will give us a distance of 51.7. So these are the distances, not knowing any of the specifics on the tie reinforcement. I slightly shifted these distances so that the tie was located at the center of the actual shear reinforcement. So you can see that some of the distances will be slightly different. With our model and all the specific dimensions that we found on the last slides, we can now find all of our strut angles just using our inverse tangent and our dimensions that we know. So we see our angle for A, C, E, and I, and J. And we can compare that with our 25-degree lower limit. And we can see that all of our angles are above 25 degrees. So our model's okay. If we had a strut angle that was less than 25 degrees, we would need to go and modify our model to make sure that we satisfy that rule. So then using these angles and the dimensions and our loads, we can figure out the different forces in our model. You can see here I determined all the forces with respect to P, and P here is a load that's applied by one of our load points. So P1 equals P, P2 equals P, and P3 equals P. So at any given time, we'll have a load of 3P on the system. So you can see that that lines up with our support reactions. Our next step is to turn to our ties. So in a design, we would need to dimension our ties. So we would come in with a known load P, and we would ensure that we have enough steel to resist that known load. For example, in tie AC, we would plug in our known load here and our yield strength of our steel and figure out how much steel we need to provide. Because we're analyzing the structure, what we're going to do is we're going to find the capacity of every element. So we'll find the capacity of every element and determine which element will control our failure. So the first tie that we'll find the capacity of is tie AC. So our tie has a yield strength of 68 KSI, and we have a total area of 12 number 11 bars. So this will give us a total capacity here of 1,270 kips. So next, to find the force required to fail this tie, we're going to set our capacity equal to our demand and solve for this load P. So our P then is going to be equal to 1,270 kips divided by 1.53, which equals 830 kips. So this means that it would take 830 kips applied on at each of our load points to fail our tie AC as it's currently designed. We can do the same thing with our ties CE, EG, GI, and IJ, all of our ties along the bottom of our model, because all those ties are going to have the same 12 number 11 bars. So we can just take that capacity divided by our demand number there and figure out that it would take 343 kips to fail tie CE, 305 kips to fail tie EG and tie GI, and 383 kips to fail tie IJ. For our vertical ties, we need to use our 25-degree and 45-degree rules that we looked at a couple slides ago. So we had already used these rules to figure out the total width of our tie, so I'm just giving that to us here. But now we can figure out the number of spaces that we have in that tie by taking our 45.5 divided by the spacing of our vertical bars in that tie region, 6.5 inches, which will give us about 7 spaces. And 7 spaces means that we have 8 bars. So 7 spaces means we have 8 bars. So then we can find the capacity of our tie by taking the yield strength of those vertical bars times, we have 2 legs of reinforcement. So 1, 2, times 8 bars, or 8 vertical bars, and then times our 0.2 square inches, which is the area of our number 4 bars. And we'll get the capacity of this tie BC equal to 192 kips. So we can again set our capacity equal to our demand and solve for the force required to fail tie BC. So we'll have 192 divided by 1.36 to give us a force here of 141 kips. So this is the force required to fail our vertical tie BC. Next, we're going to look at our tie DE, which is our hanger tie at the left load point. So the width of this tie is equal to the bearing width, 16 inches, plus 2 times our 45-degree load spread. So we can find our total width then equal to 58 inches. Using that total width, we can figure out the number of spaces that we have. So 58 divided by, we have 3-inch spacing of number 6 bars in this region. So this will give us a total of 19.3 spaces. So 19.3 spaces means that we have 20 bars in this region. So the capacity of our tie then is going to be equal to the yield strength of the steel here, which is 64 KSI, times we have 2 legs of reinforcement. So again, here we have 1, 2, and 20 bars. And then the area of our number 6 bar, 0.44 square inches. So this will give us a total force here of 1,126 kips. So again, we can set our capacity equal to our demand and solve for our force P sub DE, which will be 1,126 divided by 1.36 will give us a force of 828 kips. So this is the force required to fail tie DE. We can do the same thing for our vertical tie FG and HI and find the forces required to fail those 2 ties. So after the end of the analysis of all our ties, we can see that tie BC, it'll take the minimum load out of all the ties to fail tie BC. So this is our controlling element at this point. Our next step is to check all of our node stresses. And we're going to need to check the node stresses for our nodes with defined geometries. So in our model, that's only going to be node A and node J. If we did the cross-section models as well, then we would also need to check the load points on our ledges, but we're only going to check the stresses in nodes A and J. So both of these nodes are CCT nodes. So we have compression on the back face, we have a compression coming in from the strut-to-node interface, compression coming into the bearing face, and then we have our tension tie, which is our T. So we have C, C, T. So in this node, we need to check the strut-to-node interface, we need to check the bearing, and we also need to check the back face here. So the back face height is going to be 2 times our YS, which is the distance from the bottom to the centroid of our tension steel. So 2 times our YS of 4.36 inches will give us a value here of 8.72 inches. Our bearing length is given as 16 inches, and then we can use our equation for our strut-to-node interface length based on geometry and our strut angle. So our interface length is 16 inches times sine 41.6 degrees plus 8.72 inches times cosine 41.6 degrees, which will give us a strut to node interface length of 17.2 inches. Then our strut to node interface length for node J is going to be 16 inches times sine 26.4 degrees plus 8.72 inches times cosine 26.4 degrees, which will give us a strut to node interface length here of 15.0 inches. So we can use all these lengths with the width of our section or width of our bearing, and to find the capacity of our 3 different faces for each node. Both of our nodes of interest are CCT nodes, so we can figure out our concrete efficiency factors by this figure here. Our concrete efficiency factor for our strut to node interface is going to depend on our concrete strength. So we'll have a efficiency factor of 0.85 minus 5.7 KSI divided by 20 KSI. Gives us a factor here of 0.565. We can see that this 0.565 is between 0.45 and 0.65, so this is the value that we'll use. We're going to assume a confinement modification factor of 1.0 for simplicity, but this factor depends on how the bearing area compares to the member area that's being loaded. So if the member area being loaded is larger than the bearing area, then we can use a confinement modification. But we're just going to use 1.0 here. So our effective concrete strength then is going to be 1.0 times 0.565 times 5.7 KSI, which will give us a value here of 3.2 KSI. We can use that then with our areas that we found before. So we'll have 17.2 inches times 20 inches, our bearing width, times 3.2 KSI, which will give us a strength to node interface capacity for node A equal to 1,102 kips. Or sorry, 1,101 kips. We can compare this now to compare our capacity to our demand and figure out the load required to fail this face. So 1,101 kips divided by 2.04, the demand, which will give us 540 kips. So it'll take 540 kips to fail the strut to node interface in node A. On this slide, we'll also find the bearing face and back face capacities. So the concrete efficiency factor for both of these faces in a CCT node is 0.7, so we can fill in those values a while. We're going to assume concrete modification factors of 1.0 again. So we can then find our effective concrete strength is 1.0 times 0.7 times 5.7 KSI, which will give us a value of 4.0 KSI. So then our capacity is our bearing length, 16 inches, times 20 inches, our bearing width, times 4.0 KSI. Which will give us a capacity here of 1,280 kips. So again, finding the load required, we set our capacity equal to our demand and solve for our P. So 1280 kips divided by 1.36 will give us a value here of 941 kips. So it'll take 941 kips to fail the bearing face. Next, we can do the same thing with the back face. So our F sub CU, our effective concrete strength, will be the same. 1.0, 0.7 times 5.7 KSI, which will be 4.0 KSI. And then the strength of the back face is going to be the height of the back face, which we found to be 8.8 inches, times 20 inches, times 4.0 KSI, which will give us a value here of 704 kips. Setting our capacity equal to our demand, we can solve for the load required to fail the back face here, and we'll get 704 kips divided by 1.53, which will give us a value of 460 kips. So this is the force required to fail the back face and the bearing face of our node A. We can do the same thing that we did for node A with node J. And here, node J is also a CCT node, so we'll use the same concrete efficiency factors. And I'd fill these in since it's very similar to node A. So we find our concrete efficiency factor. Again, we're assuming a confinement modification factor of 1.0. We then find our effective concrete strength, and we can use that to find our strength of our strut to node interface. And then we can set that equal to our demand to figure out or find that we would need 260 kips to fail the strut to node interface in node J. Doing the same thing on our bearing face, we can find the capacity of our bearing face. We can also find the capacity of our back face for node J, doing the same procedure. And we can see here that the back face of the node would fail with a load of 212 kips. So this 212 kips is the controlling element in our struts. So the 212 kips controls the strut capacities, or the node capacities, but this is not less than the 141 kips that we found controls the tension ties, specifically tension tie BC. So the beam would be predicted to fail at an applied load of 141 kips, and it would be predicted to fail in element tie, or in the tie element BC. So these beams, or two tests were performed on these beams in the lab. The first test we did fail tie BC here. So this was the failure in test 1. After failure, we made sure to stop testing before too much damage was done to the beam. And then we applied additional steel through some post-tensioning clamps to a reinforced tie BC so that we could fail our node J. So you can see here that the Strut-and-Tie method did a nice job of predicting the failure. Our next step in the design procedure would be to proportion the crack control reinforcement and then also check the tie anchorage requirements. So in this, we're analyzing the section, so we were already given what reinforcement was in it. We did design these beams to have minimum crack control reinforcement. So we had 2 number 4 bars. We have a 21-inch web, so 21 inches there, times 6.5 inches, which is the spacing of these vertical number 4 bars, which gives us a vertical shear reinforcement ratio of 0.003. So this is greater than our or this is equal to, but greater than or equal to our limit of 0.003, so we're okay here. In the horizontal direction, we also have 2 number 4 bars. Our width is the same, 21 inches, and our spacing was the same, 6.5 inches. So again, we have a horizontal shear reinforcement ratio of 0.003, which is greater than or equal to our limit 0.003, so we're okay there as well. So next we need to check our tie anchorage reinforcement requirements. So we'll use our AASHTO expression for this, and we'll have 38 times the diameter of our number 11 bars, our bottom tension tie, 1.41, divided by 60 times 60 KSI, divided by the square root of 5.7 KSI, which will be equal to 22.4. We're going to assume all of our other lambda factors here are equal to 1. So our required development length for our hooked bar is just going to be 22.4. Next, we need to check our available development length against our required development length. So we'll do that by taking the given distance. So we have the distance between the centroid of our support bearing and the back of the beam was given as 40 inches, minus 2 inches cover, minus half of our bearing, gives us the distance between the back of our support to the back of our hooks of 30 inches. The available development length then is equal to that 30 inches plus our bearing length, 16 inches, plus the distance that it takes the bars to extend past or outside of this extended nodal zone. So this distance here is 2 inches times, 2 inches divided by the tangent of our strut angle, which is 41.7 in this case. So we can find that to be 48.2, which is well above our required development length. So here we have sufficient development length to be able to properly develop our longitudinal reinforcement. The final two optional steps are to first optimize the Strut-and-Tie model by returning to the modeling step. We're not going to optimize anymore, so we're going to say our model is sufficient, so we'll stop there. The last step is that we can check our service level shear cracking by using just the VC component of our sectional shear strength calculation. So we could see here that our VC is equal to 107.1 kips, and we could check this against our service demand to see if our section would crack, or we would expect cracking. But again, in this example, we're not going to do that. A summary of the loads required to fail each of the elements is shown on this slide. So you can see tie BC controls the overall failure of the specimen because it has the lowest force required to fail the element. And then because we went back and reinforced that element, the next lowest is our back face of node J, so 212. So you can see that tie BC controlled for test 1, and that is where we had failure. And the node J backface controlled for test 2, and we did have failure at node J in test 2. And you can see the actual failure loads for these and compare them, which we'll also do on the next slide. A summary of the estimated shear capacity versus the measured shear capacities is shown on this slide. So first you can see that using the VC component to estimate the first cracking load does a reasonable job. So the actual demand, or the actual load required to cause cracking, was about 34% higher than what was estimated by using just VC. In terms of the simplified procedures, you can see that in this case they were both conservative. That won't always be the case for deep beam regions, but in this case it was. And you can see that the Strut-and-Tie method was conservative in both cases, and it was closer in the case where our our node capacity control design. So shown here are the pictures of the two failures. So in the A over D of 2.5, we failed our tie BC. And in the A over D of 1.85, we failed at our node. So you can see some of the crushing that occurred there at the node. So that concludes this example problem.